-2, like 0, 1, 2, and gradually you'll move from cold, then you'll move to cool, then maybe warm, and then hot. So there cannot be a sudden change, but the change will be gradual. So this kind of a change or this kind of a decision, if you need to take this kind of a decision, the mathematical function that you need to choose or adopt is the log sigmoid function or the log sig function. Okay, the log sig function is defined as log sig of n is equal to 1 by 1 plus e to the power minus n. So this was a quick recap of activation functions and what it meant. And as I had already told you earlier, these are some of the common activation functions. So you can have the hard limiting function, the say linear function, pure lim, or the saturation linear, or the log sigmoid, or a hyperbolic tangent. These are different activation functions depending upon what kind of decision you want to take, right? So this was the biological structure of the neuron. This biological structure of the neuron has actually inspired computer scientists later on. So if you look at the history of machine learning and neural nets, you'll see that most of the work that was done earlier was done by neuroscientists. And after that, after neuroscientists, physicists and mathematicians started analyzing neural nets and maybe how to translate this biological concept to a mathematical concept. And later on, after that, electrical engineers and computer science engineers started working on neural networks. So in the 1960s and 70s, you won't find any electrical engineer, most probably you won't find electrical engineers working or computer science engineers working on neural nets. At that time, physicists and mathematicians used to work on this. So this was the basic structure of a neural net uh, that we have seen in slide number 9. And yeah, so the fundamental concept behind this is neural nets can process data in a parallel way as the human mind can. So, for example, this is input 1, this is input 2, this is input 3, and so on. So neural networks can process parallel data streams. Input 1, input 2, input 3, up to input n, the substrate n denotes the different inputs that are fed to the neural net. And after that, all these inputs get summed up over here. And after that, this F stands for an activation function or transfer function, which is nothing but the activation function just we saw right now. It is nothing but the logic that you use to take a decision, the way you process the data, and finally you produce the output. So again, quickly revising the previous concepts, we'll see this is the basic mathematical model of a single input neuron. So P represents the input to the neuron, W is the weight, B is the bias, F is the activation function, and A is the output of the neuron. So you can see what is this? This is nothing but a mathematical model of a single neuron. So this single neuron can work in a way in which your mind or your brain works. So it takes some data P. You see how how this single input neuron is somewhat similar to the working of your mind. So the single input neuron takes some input, processes it, based on some logic or activation function F, it generates an output A. So this is how a neural network actually works. So what are the terms over here? P is the input, W is the weight, B is the bias, N is called the input to the activation function, and A is the output of the activation function. So output of the activation function can be written as A is equal to F of WP plus B, because P gets multiplied by W. I'll tell you again in detail what is the meaning of weight and what is the meaning of a bias and what are the significances associated with them. So P into W, this this part becomes P into W, and you have got B. So P into W plus B. This is the net input, which goes to the activation function. And acting upon it, using some logic, you get the output A. So F of W into P plus B is equal to A. So this is the basic mathematical model of a single input neuron. So let us have a small example over here. So by giving you some small examples, maybe you'll be able to visualize how a neural network actually works and how can you calculate the output of a neural net, how the weights and the biases affect the output of the neural network. So let us take one small example. Let us say the input to a single input neuron is 1.5. So the value of P is what? 1.5. Then say the weight is 2 and the bias is -1. Okay. So I'll just copy this diagram so that you can actually relate to it. Maybe over here. Okay. So what is the question? The input is 1.5. So the value of P is 1.5. The weight is 2. The value of W is 2. The value of the bias B is -1. So what is the question? What is the input to the activation function? What is the second part of the question? What is the output of the activation function? So for example, if you see this, the value of P is given, the value of W is given, the value of B is given. What are they asking? The value of N and the value of A. So how do you calculate the value of N? So what is N? Nothing but the combined input. So P into W plus B. So the value of N is W into P plus B. We are given the value of W, that is 1.5. We're given the value of P, that is 2, and we are also given the value of B. Just substitute it. So you'll get N is equal to 1.5 into 2 plus -1. That is equal to 3 minus 1, that is equal to 2. So the value of N over here is nothing but 2. Now, what have they asked? What is the output of the activation function? So they are asking, what will you get at the output? We have already calculated what is the input over here. They are asking you what will be the output over here. But see, in this question, they haven't specified what kind of an activation function they are using. Is it hard limiting? Is it a sigmoid? Is it a log sigmoid? What is it? So they have not specified. So you can calculate the input to the activation function, but since the activation function has not been specified, you cannot calculate the output. So what is the answer to the second part of the question? The output of the activation function is not specified. The output of the activation function, or rather the activation function is not specified. Therefore, the output cannot be computed. You're not given the activation function, so you cannot compute the output. Okay, so let us say in the next example, so let us take another question. So I'll just quickly ask you, can you follow what I'm telling you? Am I going too fast? If I'm going too fast, please let me know. Can you follow what I'm telling you?
Yes, sir.
Yes, sir.
Everybody, if anybody has any doubt, please let me know, okay? Because otherwise I won't be able to understand whether you can follow or not, okay? So if you have any doubt, please let me know, okay? So yeah, so this was the first solved example. This was the first solved example in which what did we calculate? We calculated the input to the activation function, but we could not calculate the output of the activation function because the activation function was not specified. So what is the formula for calculating the input? N is equal to W into P plus B. So you just need to multiply the input and the weight, then add B. So W into P plus B is equal to N. Okay. So this is the simple formula. So let us look at another example. This is a slightly more interesting example. This will give you some insight in the working of a neural network. How does a neural network work? So this example is very important. Okay. Please try to follow. And if you have any problem regarding it, please let me know. Okay. I'll again paste the diagram over here for you. Okay. So say in this example, what will be the output if the activation function is? Now see what they are saying. They're telling you that what will be, just a second, what will be the output if the activation function is, they have given you three cases: hard limiting function, log sigmoid function, and the linear function. So you have already calculated the value of n in the previous slide. What is the value of n? The value of n is 2. 1.5 into 2 plus minus 1 is equal to 2. You have already calculated the value of n. But in the previous example, you were not given the activation function. Let us say now the question gives you the activation function. It tells you, okay, let us have three examples, three cases. First, in the first case, assume that the activation function is a hard limiting function. In the second case, assume that the activation function is a linear function. And in the third case, assume that the activation function is a log sigmoid function. In that case, what will be the output of the activation function? So we know the value of n was w into p plus b. So what was the value of n in the previous example? The value of n was 2. So what will happen if you feed the value of n is equal to 2 to the activation function? What will be the output? Let us see one by one. Let us see all the three cases, okay? So the first case, let us assume the activation function is a hard limiting function or hard lim function. So in the how is the hard limiting function defined? Hard limiting function y is equal to 1 if x is greater than or equal to 0, y is equal to 0 if x is less than 0. So this is the nature of a hard limiting function. Sudden change. So the behavior of the activation function before 0 was something else. Just after 0, it is something else. So don't you see? It's like a step. In mathematics, you would have studied about the step function in maybe school or in the 12th class or maybe in 12th standard or maybe first year of mathematics. So what is a step function? If there is a sudden change, then this is called a step function. So the hard limiting function is somewhat like the step function. So if the input is 0 or less than 0, the output is something else. If the input becomes just 0 or above or greater than 0, the output suddenly jumps to 1. Okay. So now, what is the input? What is the input to the hard limiting function? We know. What is the value of n? The value of n is 2. So let us see what will be the output of the hard limiting function if the input is 2. So see, what is the value of the hard limiting function if the input is 2? See, the value is 1. For all values 1, 2, 3, 4, 5, 6, what is the output? It is 1. What if the input had been minus 2? Then the output would have been 0. So in this case, the value of n is 2. So just let me write down for you so that it's easier for you to follow. In this case, n is equal to 2. Okay. Second, n is equal to 2. Since the value of n is equal to 2, what will be the output of the hard limiting function? See over here, the output will be 1. So the output over here, the output of this neuron would be 1. Okay. What if the value of n had been minus 3? Then see what would have been the output? In this case, it would have been 0. Okay. So am I clear with this? Can everybody follow? Does this make sense to you? Is it okay?
Yes, sir.
Okay.
Yes.
Everybody fine. So, okay, let's now see what would have been the case had it been a linear function. So, just let me so say uh, if the in the second example, say this time the activation function is not a hard limiting function, but it is a linear function. How is the linear function defined? Y is equal to x. Again, maybe in your school level or maybe in college mathematics, you would have read about the equation of the straight line y is equal to mx plus c. The linear function is nothing but y is equal to x. Whatever is the value of x, you get the same value for y. In this case, the activation function is y is equal to x, a linear function. Okay. What is the value of n? What is the value of n? N is equal to 2 over here. So if n is equal to 2, what will be the value of the activation function? You know what is the activation function? Linear function, y is equal to x. Whatever is the input, you get the same output. If the input is 2, the output will also be 2. If the input is 3, the output will also be 3. If the input is minus 1, the output will also be minus 1. So in this case, the value of n is 2. If you give this to a linear activation function, the output will also be equal to 2. So in this case, the output would be 2, right? The third example is a little more interesting. This is now, uh, yeah, this is the log sigmoid function. I don't know whether you have come across this log sigmoid function earlier or not. So this is an interesting concept. I know it is getting a little mathematical over here, but I think it's very easy to follow. It's nothing complex, right? So now let us say, you know, what is the value of the input? The value of the input, the value to the activation function is 2. So the value of n is 2. Now we need to find out what will be the output of the activation function. For that, what is the activation function in this case? It is the log sigmoid function. How is the log sigmoid function defined? The log sigmoid function is y is equal to 1 plus 1 plus e to the power minus x. I think in the previous class I had, in the previous lecture, I had already given you a list of all the common activation functions. So if someone thinks, from where am I getting these equations? So the linear is this, y is equal to, if y is equal to x or a is equal to n, the hard limiting function is something like this, log sigmoid function is something like this. So I had already given you the list of activation functions, okay? So activation functions is nothing, the way the neuron behaves. So over here, let us come back to the example. So in this case, the log sigmoid function is defined as y is equal to 1 upon 1 plus e to the power minus x. What is the value of x? What is the input? The value of the input is 2. How will you calculate the output? Just substitute 2 in place of x. Just substitute x with 2. Okay. So y of 2 is equal to log c of x, that is 1 upon 1 plus e to the power minus 2. If you have a scientific calculator, you can find out that the value comes out to be 1 upon 1 plus 0.13533, that is approximately 0.8808. So what will be the output? The output of this activation function in this case would be 0.8808. I have also tried to show this to you mathematically. This is the graph of the log sigmoid function. And if you substitute the value of 2, you'll see the output becomes 0.88. So to summarize, this was a very important example. I'll again summarize because students initially may find it a little difficult to follow. I'll summarize what I have just uh, told you now. So, if the activation function is is a step function or a hard limiting function, the output of the activation function would be 1, because for if the input is 2, the output is 1 in case the activation function is a linear function. In case the activation, sorry, in case the activation function is a hard limiting function. In case the activation function is a linear function, in that case, the output would be 2, because whatever is the input is equal to the output. In case the activation function is a log sigmoid function, the value of the output, if the input to the activation function is 2, is 0.8808. I have just calculated it for you, right? So what I need to tell you over here, what is the important takeaway? P is the input to the neuron, W is the weight, B is the bias. Based on P, the values of P, W, and V, you can calculate the input to the activation function, and based on the input to the activation function and the activation function itself, you can calculate the output of the activation function. The output of the activation function is actually the output of the neuron. In what do I exactly mean by that? This is nothing but a kind of a decision that the neural network takes. If the input is this, if the weight is this, the bias is this, what will be the output? So for different values of activation functions or the different natures of activation functions, you'll have different outputs. And different activation functions signify the different types of decisions that you need to take in real life problems. Okay. So for example, say a real life example in this case, as I just told you, for example, if the input is something like this, the output is something else. And if the input just changes above zero, then the output becomes completely something else. So there is a sudden change. In some cases, you need to take sudden decisions in life, sudden decisions. In some cases, maybe the decisions are not so sudden. You can take it gradually. Whatever is the input, you can produce it as the output. And in some other cases, the decision can be something like this. So based on different types of decisions that a machine learning algorithm needs to take, you design and use different types of activation functions. Okay. Now, I'll gradually come to some more important concepts. I'll delve deeper into some more important concepts. What is the significance of weights and what is the significance of the bias? So, in this example, you had seen that, yeah, P is the weight, P is the input, W is the weight, and B is the bias. And this is the net input to the activation function, and A is the output of the activation function. So this is how a mathematical neuron, a neural or a neural network works. But what do I exactly mean by weight? What is the physical significance of weight? What is the physical significance of bias? Let us try to understand. So, for example, in any machine learning algorithm, you can have different types of inputs. You can give a machine learning algorithm an image. You can give a machine learning algorithm, say, a video or a speech recognition system. If you have a speech recognition system, you can give it a sound clip or something. So you can give it different types of inputs. So these are the inputs which were denoted by P. What is the meaning of weight? Weight is nothing but how much importance or influence the input has. Okay. So see, the input gets multiplied by the weight. The input is P, the weight is W. You multiply P into W. So the weight is nothing but the importance or the significance of the input. If the input is very important, it is very significant, then the value of weight will be more. If the input is not that significant, the weight would be less. See, let us say if the weight is nearly zero, let us assume if the weight is nearly zero, then if you multiply any input with zero, then the value will be very less. What does that mean? Even if you change the input, it wouldn't have much of an impact on the output because its significance or its importance is very less. So weight is nothing but the significance or importance or the influence of the different inputs that you provide, right? So this is nothing but a weight. And next, we'll come to what do I mean by a bias. Okay, but before going to what do I mean by a bias, I'll try to give you one small example of the significance of weights. So we know that, say, n is equal to w into p plus b. Let us assume just for a moment that the value of the bias is zero. In that case, n is equal to w into p itself because the value of b is zero. So let us see what it actually means. What happens in this case? So let us say, in this case, say, let us assume that the input is the value of the input is 2 and the value of the weight is 2 also. So, or let us assume that the input is P and let us assume that the weight is 2 and let us assume that the bias is 0. So in this case, uh, what will be the net input? N is equal to W into P plus B. The value of bias, we have assumed it as 0. So substitute 0 over here. And the net input would be W into P. So let us vary the value of W and let us see what happens. So if the value of W is 2, then the net input will be 2 into P. If the value of W is 5, the net input will be 5P. If the value of weight is 10, the net input would be 10 into P. Okay? And let us assume for a moment that the activation function is a linear activation function. Let us just assume that the activation function is a linear activation function. So whatever you given the input, you get as the output. So let us see what is the variation in the output as you keep changing the weights. So for example, if you, I have just designed a table for you. So if say the input is 1, what is the output? If the input is 0, what is the output? I've just prepared a table for you. You don't even need to go to the table. It's pretty simple over here. So for example, if say the weight is 2, let us say the weight is 2, then in this case, what will happen, the activation function that you have in this case will be y is equal to 2x. So this is the green line over here. See, y is equal to 2x. In case the value of weight is 5, you'll have the activation function that you'll have is y is equal to 5 into x. So this is the red line over here. And in case the value of weight is 10, the activation function would be y is equal to 10 into x. See, the black line over here. So as you keep increasing the weight, the steepness of the activation function increases. This is the graph for y is equal to w is equal to 2. This is the graph for w is equal to 5. This is the graph for w is equal to 10. So as you keep increasing the weight, you see what happens is the steepness, the slope of the straight line keeps increasing. What does that mean? It means the strength of the linear function keeps increasing. So I'll just give you a small example. Maybe, yeah, this will help you understand this. So see what happens. As you keep increasing the weights, the steepness of the activation function keeps increasing. The steepness increases. This means that the impact of the impact of the activation function is much more. Now we'll try to understand what is the significance of the bias. What happens if you change the bias? So I just told you these are the different inputs to the neuron. These are the weights associated with the inputs, and there is something called a bias. What is this bias now? I'll just give you one small example. Let us have a very small example. So maybe say, I'll just write it for you maybe. So let us say, uh, okay, uh, maybe, I guess all of you are college students over here. So maybe you see movies sometimes. I hope sometimes when you find time besides your studies, you watch movies also. So for example, let me say that the input is a movie. Okay, am I audible to all of you?
Yes,
I
sir.
hope I
Yes,
hope
Yes,
sir.
I am
sir.
audible to all of you. Fine. So I'll just take a small example. So let us say the input is movies. So now there are some people who are very passionate about movies. So whatever movie is released, they see that movie. Whatever movie is released, Hindi, English, whatever movie is released, they watch that movie. Okay. But maybe some people are a little more selective. So say if the movie has, say, for example, their favorite actor. Let us say their favorite actor is, let us assume, Ritik Roshan. Or let us say, first of all, they're selective about movies. They see only, say, Hindi movies. So maybe there is some person who just likes to watch Hindi movies. He or she doesn't like to watch English movies or French movies or something. So you are becoming a little more uh, selective over here. So there may be some people who will watch any movie that is released. There may be some more people who are a little more selective. If the movie is a Hindi movie, they'll watch it. Otherwise, they won't watch it. Now you can be a little more selective, and if you say that if say the movie has say their favorite actor, say let us say the favorite actor is, let us assume, for example, Ritik Roshan. Okay, from an Indian perspective. So let us say their favorite actor is Ritik Roshan. Okay. So there may be some people who will watch the movie only if Ritik Roshan is a part of that movie, if Ritik Roshan has a role. So there can be three types of people. Category one, who will watch any movie that is released, Hindi, English, Punjabi, Marathi, Tamil, any movie, they'll watch any movie. Now, next, there can be some people who will watch only Hindi movies. So they'll not jump to watch a movie. They'll first see whether the movie is a Hindi movie or not. Otherwise, they won't see the movie. The third category the people may be even more selective. They'll wait. Okay, let me see. Is this a movie? Yes. Is this a Hindi movie? Yes. Is my favorite actor a part of that movie? Is Hrithik Roshan a part of the movie? If the answer is yes, only then will they watch the movie. So they won't suddenly take a decision. Maybe they'll wait. Okay, they'll wait to analyze all the parameters and they'll take an action a little later. Okay, so in this case, what I was trying to tell you is different inputs are necessary to actually decide what you're going to do. Different people decide things differently. So, for example, an input may have some additional attributes. So, if you add Ritik Roshan to the movie, if you add the Hindi category to the movie, then the importance of the movie may change. So, for example, in place of Ritik Roshan, if there is some other actor X, maybe whom you don't like, then you maybe you won't watch the movie. So, this input, this is a weight, this is the weight to that input. The weight is nothing but the importance of that input, the significance of that input. Okay, this is the weight. Now, next come to the example of a bias. Okay, bias. So, for what do you mean by a bias? Bias means when you are taking the decision. When do you want to take the decision? That is governed by the bias. What do I mean by that? So let us say, let us take one example again. Let us say, uh, if I give you, maybe you get a movie ticket. Okay, let us take one simple example. You get a movie ticket. Okay, and say after a week you have got your exams. Okay, so maybe you'll take a little time to decide whether you want to go and watch the movie or not. If you really want to go and watch the movie, if the movie seems to be very important to you, you're really interested in the movie, maybe you'll go. But in what I mean to say here is maybe you won't take the decision suddenly. Maybe you'll take the decision a little later. You'll think about what to do, and after that, you'll take the decision. So there is something called bias. The bias actually governs when the activation function is going to be triggered. So what does the activation function do? We know that what the activation function does is over here, just a second, I'll just go back. So I'll just go back. Yeah. So for example, I told you, what does the bias do? Uh, so P is the input, W is the output. The output is P is the input, W is the weight. So weight is the importance or the significance of the input. What does the bias do? The bias actually governs when the activation function will be triggered. That is, when the decision will be taken. Will the decision be taken immediately or the decision will be taken a little later? That is governed by the value of bias B. Let me give you one example, then maybe you'll understand it more clearly. Say, this is input 1. It has got some importance weight or weight W1 or weight 1. This is the input 2 and it has got some importance weight 2, W2. And this bias decides when the decision by the activation function will be taken, whether it will be taken immediately or whether it will be taken a little later. So when the activation function will be triggered is governed by the bias. So maybe I'll just give you one small example over here. So let us say the input to the activation function is, as we have seen, is n is equal to w into p plus b. And let the activation function be y is equal to n. So I have given you one example. So let us take three examples. Let us say the bias is 0 in one case, the bias is 2 in the next case, and the value of the bias is minus 2 in the last case. So let us see what happens. So let us say the input is P, the weight is W, bias is minus 2 in one case, 0 in the other case, and 2 in the last case. So if the activation function is a linear function, what will be the input to the activation function? In the first case, it will be w into p minus 2. In the next case, it will be w into p, since the value of bias is 0. And in the third case, it will be w into p plus 2. Okay. So when will the activation function start working? So as you will see, for example, if you substitute w into p minus 2 is equal to 0, you'll get p is equal to 2 divided by w. If w into p plus 0 is equal to 0, then p is equal to 0. I'll tell you what this means actually. And if w plus 2, w into p plus 2, this is plus 2, plus 2 is equal to 0, you will get p is equal to minus 2 by w. What this means, the activation function, if the value of the bias is minus 2, the activation function will be triggered at, say, p is equal to 2. If the activation function, if the value of the bias is plus 2, then the activation function will be triggered earlier. I'll just give you the graph, you'll maybe understand better. For example, see, in case the value of bias is 0, then the activation function, the linear activation function, passes through the origin. Okay, this passes through the origin. In case the bias is minus 2, in case the bias is minus 2, the graph shifts over here. See, over here. So what was happening over here, what was happening at 0 will now happen at minus 2. If the value of the bias is 2, then the graph will shift here. So what was happening at 0 will now happen at plus 2. So this is the complete picture over here. Rather than going into too much of mathematics, maybe you can very easily understand it through the graph. If the value of the bias is 0, if the value of the bias is 0, say the activation function starts working at 0. If the value of the bias is minus 2, then the activation function starts working over here at minus 2. So see, there is an advance. What was happening here is actually happening here. It has shifted over here. So there is an advance. You're doing it more quickly. You're taking a much earlier decision. If the value of the bias is plus 2, this graph shifts over here. This is a delay. Okay, so you'll wait. Maybe you'll wait for 2 hours. Okay. So in the normal condition, this is the activation function. You take the decision over here. In case there is a bias of minus 2, you take a quicker decision. You take it earlier. In case the value of the bias is plus 2, you delay your decision. So you can either delay your decision or you can advance your decision. That is based on the bias. So similarly, in the neural network, or in case of a neuron, the bias decides when the decision will be taken. Will the decision be taken as soon as the inputs arrive, or will the decision be taken a little later? Will you advance the decision making process, or will you delay the decision making process? That is governed by the bias. So I'll give you one small example of the bias as well. So there is a good image that will give you a good example. See what happens. So what the bias does is it adds an intercept to your straight line. So let us assume the activation function is a linear function. As you keep increasing, so see what happens is it shifts left. What was happening here keeps shifting over here. See, it shifts over here. What does that mean? It means you're taking the decision earlier. Similarly, you could have also taken the decision later had the graph gone below this. So this is the meaning of the activation function and the bias and the weight. So what does the bias do? It tells you when to take the decision, early or late or at the same moment. Okay, fine. So now these are some things. These are some of the concepts which I've already discussed. So you can have one input to the neuron, or you can have multiple inputs to the neuron as well. Parallel inputs P1, P2, P3, P4, P5 up to PR. In this case, all the inputs will get summed up over here. Then you will multiply the individual weights. Every input will have a weight. So P1 will have a weight W11, P2 will have a weight W12, P3 will have a weight W13, and PR, the input, will have a weight W1R. So what you'll do is multiply each of the inputs to the weight, then add the bias, then based on the activation function, you'll get an output. Uh, Now you can have, in this case, it was say multiple inputs to a single neuron, but you can have multiple neurons as well. This is one neuron, this is one neuron, this is one neuron. You can have different biases. The bias to this neuron is B1, the bias to this neuron is B2, the bias to this neuron is say BS. There are multiple inputs which are going to multiple neurons. See, this first input is going to the first neuron, the first input is also going to the second neuron, the first input is also going to the Sth neuron. So this input is connected to this neuron, this neuron, this neuron. Similarly, the second input is also connected to this neuron, and this neuron. So this is how multiple inputs can get connected to multiple neurons, and the different neurons can have different bias values. The different neurons may have different activation functions also. And similarly, you'll have multiple outputs of a neuron. So you can have multiple outputs from a neural network as well. It's not necessarily that only one output from a neural network. For example, you let us take one practical example. Let us say you want to classify an image. So I give you an image and you have to classify it into say five categories. Whether it's a car, whether it's a bike, whether it's a human, whether it's a house, or whether it's a bus. So you have got five categories. So the neural network can have multiple outputs also. So in such examples, you need to have multiple neurons, right? So in this case, you'll see there will be multiple weights also. So if the first input is connected to the first neuron, the weight would be W11. If the first input is connected to the second neuron, then it will be W12. Similarly, if the Rth input is connected to the Sth neuron, then the weight will be Ws comma R. All the inputs will be multiplied by the corresponding weights, and then the bias gets added. Then based on the activation function, you get some output. So in this case, you'll see the weight is not fixed. The weight is not a unique value, but it's basically a matrix now. So it will range from W11, W12, W13, W1R. Similarly, W21, W22, W23, W2R, and WS1, WS2 up to WSR. So this is an S comma R, the S cross R matrix. So the weight will now be a matrix. So generally what happens is when you give multiple inputs to a neural network, the weights keep updating and generally it's in the form of a matrix. Okay, so this is a layer of neurons. And now we'll maybe go into a little more detail. If anybody feels any difficulty in understanding, please let me know. Okay, if you think I'm going a little too fast, let me know, I'll slow down or give you some other examples. So basically, in the previous section also, I had given you this example. So this is the internal structure of a neural network. Generally, these are the neurons. There is an input layer where the inputs arrive. Then there is a hidden layer. The processing of the data is done, and this is the output layer from which you get the output. Input layer, hidden layer, output layer. Now, some neural networks can have multiple hidden layers also based on the amount of data processing that you need to do and based on the inputs. That if the inputs are too large and you need to do a lot of processing, you may have multiple hidden layers as well. So I'll just give you one example of that. Multiple hidden layered neural network. So see, this is the first layer. These are the inputs. This is the first layer. This is the second layer. This is the third layer. So you'll see all the layers are cascaded one after the other, one after the other. The output of the first layer goes to the second layer. The output of the second layer goes to the third layer. So the output of one layer becomes the input of the other layer. See? So different layers. This is layer one, this is layer two, this is layer three. The different layers can have different activation functions. Generally, we try to design neural nets with deep neural nets with different activation functions so that their performance can be diversified. So see, this can have a different activation function, different values of bias. This can have different activation functions, different values of bias. This can have different activation functions and different values of bias. So you'll see the output of this neuron or layer of neurons goes to this second layer, and the output of the second layer goes to the third layer, right? So this is how you can write the output. For example, see, f of 3 becomes w of 3 into f of 2. So the output of the second layer becomes the input to the third layer and so on. So generally, these type of neural networks with multiple hidden layers can serve much more purpose. We'll just take one example maybe. So let us take one example. Let us say one of the layers has the activation function as a sigmoid function, and the second layer has an activation function as a linear function. Let us assume that, and let us see what we can do with it. So let us say the first layer's activation function is a sigmoid function, and the second layer's activation function is a linear function. Let us see what we can do with that. What is the significance? See, what does the sigmoid function do? This is not the log sigmoid, this is a simple sigmoid. So, for example, this sigmoid function, if you'll see, uh, uh, what it does is, if you look at the nature of this, if the input is greater than say 0 input, then the value would be greater than 0.5, and if the input is less than 0, then the value would be say less than 0.5. On the contrary, you can also think it to be like this: for values greater than 0.5, see the behavior of the function. It tries to move towards 1. For values less than 0.5, it tries to move towards, say, 0. So, for example, don't you think it can be used as an approximator? How, for example, for example, if I give you a value 2.8, how will you approximate it? You'll say 2.8 approximates to 3. So, just let me write it down for you so that it becomes a little easy to follow. So for example, say I write, if I give you 2.8, how will you approximate it? Maybe you'll approximate it to 3. If I give you say 2.1, you'll approximate it to 2. If I give you say 2.6, maybe you'll again approximate it to 3. So anything above zero point 0.5, you'll approximate it to the next integer. And if the fraction part is less than zero point 0.5, you'll approximate it to the previous integer. So see, this is something that can be done using this sort of function, because less than, if the value is less than zero point 0.5, the nature is something else. If the value is greater than 0.5, the nature is something else. So this is how, see, what you can do is, this is how you can actually use different activation functions to approximate values. So maybe above zero point 0.5, I'll go to the next value. And if it's less than zero point 0.5, I'll go to the next value. So zero point 0.5, above zero point 0.5, I'll go to 1. And less than 0point 0.5, I'll go to 0 and add it to a linear function. Say it is 2.5 or 2.6. So what this will do is, since it's zero point 0.6, it will add 1. So 2 plus 1 is 3. So it'll approximate it to 3. If it say 2.1, so it's less than zero point 0.5, it will be 0. So it add to 2. So adding it to 2 becomes 2 plus 0 is 2 itself. So maybe if you design a neural net with one of the activation functions, say one of the activation functions of one of the layers being the sigmoid function and the other being the linear function, you can actually design an approximator. Okay, so this is how you can use multiple layers and multiple activation functions and transfer functions to actually design different types of applications, right? Uh, I think this is okay with your the basic theory of neural nets, the bias and the weights and the activation functions, different layers, its significance. And now let's move to something, a different topic called regression. Okay, so this is not that complex mathematically. Maybe it's a little simpler compared to neural nets. Yeah, am I audible to everybody? Is everything okay on your side?
Yes, sir.
Done, done. Okay. I know it was a little bit of mathematics that I had put in, a little bit of complex maths that I had put in. So maybe now maybe we are moving towards a little lighter side and much more practical examples. So this session, the next 1 hour maybe would be a little easier for you, maybe. So anyway, so let us say regression. Now let us take some real life examples and you'll maybe enjoy a little more. So let us say what do I mean by regression? So regression problems, there are basically two main types of problems that we need to, although there are different types of problems that you can deal with neural nets or machine learning. But regression is one of the most important problems that you try to solve using neural nets or some other machine learning algorithms. So let us take one example. So let us say this is a variable which is the area of a house in square feet, and this is the price of the house in lakhs. So let us say there is a house or there is an apartment whose area is 700 square feet, and say its price is 10 lakhs. If the area is say 750 square feet, then let us say the the price is 12 lakhs. 900 square feet, 15 lakhs. 950 square feet, 16 lakhs. 1200 square feet, 20 lakhs. 1500 square feet, 25 lakhs, and so on. So do you see one thing? As you keep changing the area of the apartment of or house, the price of the house also changes. So don't you think that the price of the house is a function of the area? So I'll just write it for you maybe. So I'll just write it for you. So say the price is a function of the area. Yeah, definitely. The larger the area is, the higher the price is. And you may also say, okay, sir, this is not only an example which has only one variable. You can have, say, the price may also depend on the location or some other parameters also. I do agree, but right here, I'm just considering only one parameter based on which the price depends. So maybe price can be one of the parameters. This is also called a feature. So now, what I want to do, I want to find a relation between the area of the house and the price in lakhs. Area and the price. What is the relation between the area of the house and the price, so that I can create a model in which I'll enter the area and I'll get the price. So over here, say if I can somehow create a model from this, if I can somehow create a model from this, what will happen is in that case, what I'll do, I'll enter the area and I will get the price. This is what I want to do. So first of all, I need to find a relation between the area of the house and the price. So in this is called the independent variable x, and this is called the dependent variable y. What do I mean by linear regression? So I'll come to the next slide now. Come to the next slide now. So in case of linear regression, what we need to do is we generally try to find a relation between the input variable and the output variable. So let us say the input variable is x, that is the price, that is the area, and the output variable is y, that is the price. Okay. So for example, I want to find a relation between x and y. Theta 1 and theta 2 are called the coefficients of the regression model. So in this case, you can see what is the highest power of x over here? It's 1. So if you try to recall, if you try to compare y is equal to theta 1 plus theta 2 x, you'll see that this is in this format, y is equal to mx plus c. So basically, the relation between x and y is nothing but a straight line. Okay. So in that case, uh, say for example, I'll just so if this is x, and say if this is x, this is y, and the relation between x and y will be a straight line. Okay. So in case you try to create a model in which the relation between x and y is a straight line, then it's called linear regression. It may so happen that the relation is not a straight line. It can be a non-straight line as well. So for example, say it is something like this, maybe it is something like this. In that case, this is an example of a non-linear regression model. So the regression model can be a linear regression if you can find out, for example, say just a second, if you can find out a relation between x and y which follows a straight line, then it's called a linear regression model. And if you cannot find a straight line, or if the relation is non-linear, then it's called non-linear regression. Okay. So these are some important concepts over here. I'll gradually come to these. So, fine. So the next concept I hope you can follow what I'm trying to tell you. I hope this makes sense. You are trying to find a relation between the area and the price. So the relation can be a linear relation. The relation can be a non-linear relation. If the relation is a linear relation, like y is equal to mx plus c, then it's called linear regression. If the relation is a non-linear regression, relation, then it's called a non-linear regression model. So I'll come to those as well. So let me do one thing first of all. Maybe let me give you a few examples, then maybe you'll understand better. So let us have a few coding examples first of all. So you'll understand linear regression better with that. So yeah, let us start with bias and activation function. So let us start with, I'll share all the coding examples so you can just see what. So first of all, let me go to the weights example. So for example, uh, I'll give you an example. For example, see over here. Yeah. So for example, this is what I had given you. As the weights keep changing, the steepness of the activation function changes. So this is how you can say the weights signify how strongly the activation function will behave. This is what we have already seen. In the next example, maybe we'll try to see what is the effect of the bias. We have already seen this. Just to reiterate. So this is the effect of the bias. What it does is it shifts the activation function. Either it delays the activation function or it advances the activation function. This is the effect of the bias. No bias, decision is taken like this. A bias of 2 is shifted. A bias of -2, it is again shifted. So either you can advance your decision or you can delay your decision. So this is the effect of the bias. Now let me come to the linear regression example. So you'll maybe understand even better. So let me go to the linear regression. So for example, this is interesting. So say, okay. So let us see what this all is. Let me go say maybe step by step. So basically what I have done over here, if we go to the code example, I have loaded an accident data set, and I'll try to find out what is the relation between the population of a state and the number of accidents taking place. So let us try to understand. So see, first of all, this is a linear regression example. So I'll load the accident data sets, and these are the headers. What are the headers? I'll tell you. So let me first of all say load this command for you. This is so see what I've done is load accidents. So this is the data set, accident data set, and these are the headers. So you'll see what are the headers basically. If you say, for example, go to this. This is basically a 1 cross 17 array. So this entire data has one row and 17 columns. The 17 columns have different values or have different parameters. Say the seventh is the vehicle miles traveled. The number of miles the vehicle travel, registered vehicles, the number of registered vehicles. For example, in any state, if there are unregistered vehicles, then maybe the possibility of accidents is more. If the vehicles are registered, maybe the possibility of accidents is less. Maybe. Uh, Fatalities per 100K licensed drivers. There can be different variables, different parameters which decide the number of accidents which are going to take place. So I'll just give you this example. Maybe you'll maybe be able to figure out more clearly. So the 14th column is the population of the state, and the fourth column is the accidents per state. So let me try to just say load this. So
Excuse me, sir.
yeah, exactly.
We are only showing the PPT slide.
Oh, is the MATLAB not visible to you?
No, no, sir.
Okay, just a second. Just a second. Okay. So,
Yes, sir. Now it
is
is.
MATLAB visible now?
Yes, sir. Yes.
Okay, maybe I was sharing the PPT. I wasn't sharing the screen, maybe. So, okay, let us start again. Okay, just a second. I'll start with MATLAB. I didn't know this. Anyway, so is MATLAB visible to you? Everybody, can everybody see MATLAB now?
Yes, sir.
Yes, sir.
Fine. Maybe you can see the screen now. Okay, I just went through two examples. I'll just quickly go through those two examples, although they have been already been explained. So this is the effect of weights, or rather, let me not take this example now. Let me directly go to the regression problem. So see where were we till now? We were trying to find out the relation between variables. This is nothing but a regression problem. So if you can find a linear relationship, then it's called linear regression. If you can find a non-linear relationship, then it's called non-linear regression. So the value, the type of relation you find between the input variable and the output variable governs the type of regression that you have. So it can be a linear regression in the form of y is equal to mx plus c, or it can also be a non-linear regression. It depends. So now uh, I'll go to the coding example. Actually, I was going to the coding example. Let me see the linear regression example first of all. So I have got, can you see this now? Is this visible to you? Is the code
Yes,
visible to
sir.
you? Yeah.
Yes, sir.
So what I'll do is I have got an accidents data set. It is already an inbuilt data set in MATLAB, and it has got several parameters. Just let me load this for you. So load accidents will load the accident data set. Uh, HY headers. This means what are the different parameters, what are the different headers in the data set. So the 14th column of the cell or the array is the population of the state, and the fourth column is the accidents per year in the state. So what we'll do, we'll try to find out a relationship between the population of a state and the number of accidents in the state per year. So let us see if you can do that. So yeah. So there are multiple parameters, say number of registered vehicles, number of licensed drivers, fatalities per 1,000, maybe 100,000 vehicles, different parameters, but we are only interested in calculating the relation between the population of the state and the accidents in the state. So we are just interested in calculating a relationship or finding a relationship between these two parameters. Okay. So what we will do is we'll try to find out a linear regression model. So as you know, the linear regression model, what kind of a relation does it follow? It follows a relation y is equal to theta 1 plus theta 2 into x. So over here, this x is the independent variable and y is the dependent variable. So the independent variable is the population of the state, and y is the dependent variable. It is the number of accidents in the state. Maybe you'll guess that more the number of people in a state, that more the population is, more will be the number of accidents. Maybe overpopulous state, more accidents. We'll try to find out a relationship between the number of accidents and the population of a state. This is what we're trying to do. So in that case, first of all, let us do one thing. Maybe from school mathematics, you know that y in the equation y is equal to mx plus c, m is called the slope and c is called the intercept. So m is nothing but y by x. Okay. So in this case, what we'll try to do, we'll try to calculate two variables, theta1 and theta2, and we'll try to see how we can get a relationship between these two variables. Let us try to find out the value of b first of all, that is x by y. So let us try to find out the value of b first of all. The value of b1 comes out to be 1.372 e minus 0.4. What does this mean? 1.3727, this big value, into 10 to the power minus 4. So to write 10 to the power minus 4 in MATLAB, we write e minus 0.4. Okay, so this is how it is written. So e minus 0.4 means 10 to the power minus 4. The value of b comes out to be 1.372 something 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 into 10 to the power minus 4. So this is the value of b. This is one of the coefficients. This is nothing but one of the coefficients. So what we'll try to do now is, I'll tell you what I'll try to do. What I've done over here is, if you follow the code, I have multiplied b1 with x. Why? Because I am first of all trying to design a regression model in the form y is equal to mx only. Later on, what I'll do is I'll try to design a model y is equal to mx plus c. Can you follow? Is it okay? What I am doing over here is I am trying to design a model with c is equal to 0. So I'll try to design a model y is equal to mx. And later on, what I'll try to do, I'll try to design a model y is equal to mx plus c. So I'll try to compare both the models. I'll see which model is more accurate. I have a very small question for all of you. Maybe just to wake you up. Which model do you think would be more accurate? Y is equal to mx or y is equal to mx plus c? In this case, what is your guess? Any guess? Which model do you think would be more accurate? Y is equal to mx linear model or y is equal to mx plus c linear model? What do you think?
MX
Anybody?
plus C.
equal to mx plus c.
Why? Okay, maybe a lot of people are saying y should mx plus c. Why do you think so? Why will mx plus c be more accurate?
So
Why do you
maybe
think
it
so?
will decrease. So maybe it will decrease the errors.
Okay, see, what happens is, maybe in most cases, y is equal to mx plus c will be more accurate. You are right in that sense. But to understand why it would be more accurate, let us look at this equation. Let us go back to the PPT. See, say you have a relation which has y is equal to mx only. You don't have the value of c. That means you are missing one of the coefficients of the model. You are missing one of the values. You have to model it just as y is equal to mx. But if you have y is equal to mx plus c, you have got another variable which can fit the model even better. So in that case, y is, in most cases, y is equal to mx plus c will fit the model better because you have got another variable or another coefficient over here. So y is equal to theta1 plus theta2 x would be more accurate than y is equal to theta2 x alone. Obviously, because you have an additional variable theta1, which will help you in modeling the or fitting the model better. So in obviously y is equal to mx plus c will generally be more accurate than y is equal to mx. Okay. So let us try to find out. So this graph over here is the graph for y is equal to mx only. So this is the graph for y is equal to mx only. So what I'll do now is I'll now go to y is equal to mx plus c. So I have appended some ones over here. Once, this is a command in MATLAB to append or add ones. And after that, what I'll try to do is I'll try to go with y is equal to mx plus c. So let us see what happens. I'll run the entire code now. See what happens. So you'll see over here. Is my screen visible to everybody?
Yes, sir.
Okay. So can you see two graphs over here? Two overlapping graphs. So these blue dots are the data points. What is the x-axis? population of the state. What is the y-axis? Fatal traffic accidents per state. So x-axis the population and y-axis the number of accidents. Can you see a common pattern? As the population increases, the number of accidents also increases. Can you see this? See? Is it visible to you? Is it visible to everybody? Does
Yes,
this
sir.
make sense? Can you
Yes,
follow?
sir.
As the population increases, see, as the population increases, the line is going upwards. That means the number of accidents also increases. And these are the actual data points. For example, if this is the population, say 1 million, so this is actually 10 to the power 7, that is in crores. If the population is 1 crore, then what is the number of accidents? Slightly above 1000. If the population is, say, around 2 crore, then the number of accidents is around 1500. If the population is around about, say, 3.5 crores, see, what are the number of accidents? Around about, say, 4200. So as the population increases, into 10 to the power minus 7 is like crores. As the population increases, the number of accidents also increases. Now we are trying to find a linear relationship between the population of the state and the accidents, and we have used two models over here, two linear regression models. One has only the slope and one has the slope plus intercept. So the one which has the slope itself is y is equal to mx. So I'll just write it down for you. So yeah, so this thing over here, this is y is equal to m into x, because the slope is given by m. The slope is denoted by m. Slope plus intercept means y is equal to m x plus the c. Now c, writing c is a little difficult over here. For example, I should have used this thing. This one. Is y is equal to mx plus c. So this slope plus intercept means y is equal to mx plus c, and only slope means y is equal to mx. So you'll see that there are two lines over here. One is this line and one is this dashed line. So this is the line for y is equal to mx plus c, and this is y is equal to mx. So this is, you can also say it as y is equal to theta 1 plus theta 2x, and this is only y is equal to theta 2x. This one is actually more accurate. How? Let me just prove it to you. If you see, I have calculated two values over here. R square, I'll tell you what this means. This is the regression value. For the first case, y is equal to mx, the value of regression is 0.82223 and etc. It's a long decimal value. And for the second case, it's 0.83. So which is higher, 0.82 or 0.83? 0.83 is greater. So this is called the value of regression. The maximum value of regression is 1. 1 means complete similarity, and any value which is closer to 1 gives you higher similarity. So for example, this is a more accurate and better fitting model. When we go to the next example, you can see it even more clearly. You can visualize it more clearly. So what I would like to ask you to see over here is the value of regression is lesser in this case for y equal to mx. The value of regression is greater in this case. So the second model, y equal to mx plus c, is more accurate. How is it more accurate? I'll tell you. So let's go to the next example. This was the linear example. I hope my screen is visible to everybody. Is my
Yes,
screen
sir.
visible? Yeah,
Yes,
yeah.
sir.
Okay, done. Yeah. So let us go to another example. Let us say the house price example that I was talking about. Let us say this is the area of the house, this is the year, and this is the price in lakhs. Say the area of the house is 1000 square feet. In the year 2010, the price was 10 lakhs. In 11, it became 11 lakhs. In 2012, it became 11.9 lakhs. Let us say if the area of the house is 1200 square feet, in 2010, the price was 14 lakhs. In 2011, the price became 14.5 lakhs. And in 2012, the price becomes 16 lakhs, and so on. So this is something, this is a data, a very small data set. I have actually randomly created this data set. This is a data set, and I want to find out the relation between the area of the house and the price, and also the year and the price. I want to find this out. I want to find out the relation. So what I'll do is, I'll design a very small regression problem or regression model. So what I'll do is, first of all, the first command that I'll write is data is equal to xls read house price dot xlsx. This is a MATLAB command which will read the Excel file for me. Okay, so let me see if I can read the Excel file. I'll first of all clear all the variables. Yeah. So I have what I have done is I have tried to read the Excel sheets values. So if I go to data, I can see this is a 12 cross 3 matrix. See, it was a 12 cross 3 matrix. It has got 12 rows and 3 columns. Okay. This is the area. The first column corresponds to area of the house. The second column corresponds to year, and the third column corresponds to the price. So you'll see the first column over here. First column corresponds to the year area. Second column corresponds to the year, and third column corresponds to the price in lakhs. Okay. So I want to find out a relation. I want to visualize. First of all, I want to visualize the relationship between the variables. Okay. So let me see if I can do that. So this XLS read command, I guess you could see this. This XLS read command helps me to read an Excel file and import the Excel file to the MATLAB workspace. And after that, let me do one thing. Let me first of all separate the matrix into 3 different vectors. So the first column is the area, second column is the year, third column is the price. So what I'll do is I'll maybe define a variable area is equal to data colon 1. That means the first column of the variable data corresponds to the area. The second column of the data corresponds to the year. Third column of the data corresponds to the price. So what I'll do is I'll define 3 more variables for you. So I've got 3 more variables. The first column is the area. First column is the area. Second is the year, and the third column is the price. Okay, fine. Now what I'll try to do, I'll try to figure out a way to visualize uh, the dependence of the area and the price. For that, I'll plot something called a scatter plot. So the command for this figure will open up a new figure, and then the scatter will open up a scatter plot. You'll see what a scatter plot looks like. I hope you can see this. See, uh, when the area was like 1000 square feet, we had different prices, 10 lakhs, 11 lakhs, and 12 lakhs for the 3 years. When the area was 1200 square feet, there were again for 3 years there were three prices. So this is how you can see as the area of the house increases, the price also keeps increasing. See, the price keeps increasing. How you can see the relationship? You can go to tools, then basic fitting, then you can go to say linear. See, can you see now? So this is kind of a linear relationship between the area of the house and the price of the house. You can also have a non-linear relationship like a quadratic relationship, something like this. You can also have a cubic relationship, something like this. So you can have different regression models. In the regression model aims at finding the relationship between two variables. In this case, it is the relationship, we are trying to find the relationship between the area of the house and the price of the house. So you can have a linear relationship, you can have a quadratic relationship, square, and you can have a cubic relationship, that is a cube, third power. So this is how you can find the relationship between the price and the price and the area of the houses. Now, if you can do another thing, what you can do is you can also try to find out the relationship between, say, the year and the price. Again, you'll see this x-axis corresponds to the years, y-axis corresponds to the prices. So as the years keep increasing, you'll see the prices also keep increasing. Okay, so this is the concept of a scatter plot. So you can also plot both things at the same time. So the command for a scatter plot is scatter. If I write scatter area comma price, that will plot a scatter plot for the area and the price. And K stands for the color of the scatter plot. K stands for black color, R stands for red color. And I can also plot these both things at the same time. So in this case, you'll see this x-axis has the years. Uh, this this x-axis has the area, y-axis has the years, and these are all the points. All these points tell you. Say, for example, this point tells you the area is 1200 square feet, and the year is 2011. So these are the different points. So this scatter plot gives you an idea about the relationship between the dependent and the independent variables. This was one simple example of the house data set. So maybe I'll try to go to the next example. Linear and non-linear regression values. So let me see if I can actually plot a linear and non-linear regression values for you, model for you. So if we, for example, if we look at a non-linear model, so in this case, see, I have initialized loop for I is equal to 1 to 100, index I, x is equal to I square. So then I'll generate some random numbers. Rand nr will generate random numbers. I have multiplied the random numbers by 1000 so that I can add some noise or some disturbances to the data. And what I'll do is I'll add this noisy part to the data. So the data is x square for x is equal to 1 to 100. So this is a square function. Then we'll add some noise to the data, some random disturbances, and let us see how the data looks like. This may be like a real-time data, real-life data. So is this visible to everybody? Is this visible to everyone?
Yes, sir.
Yeah. So maybe in this case, I again want to ask you a question. I again have a question for everybody. Do you think you can have a linear regression model for this data set. What do you think? This is my question to everybody. Do you think that you can have a linear regression model for this data set? Do you think so? In other words, can you describe this data? Can you model this data in terms of a straight line? Is it possible? Do you think so?
No, sir.
Yes or no? I couldn't get you.
No, sir.
No, it's
No,
difficult.
sir.
Yes. Yeah, not possible. Let us see. Let us try both things because it's moving like a square function. Let us see. Say, let us try out the linear function first. See, the linear function is not very accurate. See, is it accurate? No, it's not very accurate. Let us go for the quadratic function. See, the quadratic function is much more accurate. Is my screen visible to everybody?
Yes, sir. Yes, sir.
See, this data, does this data follow a linear pattern? Does this data follow a linear pattern? No, this data does not follow. Had this data followed a linear pattern, these data points would have been on this straight line. But are the data points on the straight line? No, the data points are not on the straight line. Rather, the data points lie near to the quadratic graph. That means this data set cannot be modeled. This is a very important statement that I'm making. This data set cannot be modeled using a linear regression model. You have to go for a non-linear regression model in this case because of the nature of the data. In data science or in machine learning, you get different types of data sets. Some data sets may follow a linear pattern. Some data sets may not follow a linear pattern. It's not necessary that in every case you'll be able to model the data in a form of a linear regression model. It's not so. In this case, in this example, you just saw that in this case, the linear model does not work. The quadratic model works. That is the second square. That is square, the second power of the independent variable. Okay. So this is something very important, an important takeaway. So after this coding example, maybe I'll, yeah, next. Okay. So this was about the linear regression model and objective function. Okay. So the next point is the concept of retraining. We have got around about 20 minutes left for our session to get over. So the last two or three concepts are very important actually. The first concept is retraining. Generally, what happens is, what do we mean by retraining? Generally, any machine learning model, whether it's a neural network or a linear regression model or a non-linear regression model, support vector regression model, any sort of model, generally what happens is, as you feed data to the model, it tries to find out some relation between the inputs and the outputs. Okay. So what happens is, generally, if you feed the data once, then we say that you have trained the model. If you give the machine learning model the data for the first time, you say that we have trained the machine learning model for the first time. That is the first iteration. If you again give the machine learning model the data, then we say that we have retrained the machine learning model. That can be the second iteration. Similarly, you can retrain it multiple number of times. Why do we need to retrain it? Let me give you one practical example. Suppose there's a mathematics class and students of 9th standard are learning trigonometry. Day 1, trigonometry, sine theta, cos theta, tan theta, sine squared theta plus cos squared theta is 1, etc. First day of trigonometry, the teacher teaches trigonometry. In the first day, maybe all the students may not be able to grasp all the concepts of trigonometry in the first day itself. So maybe on the first day, the teacher takes a small test after finishing the topics. And maybe the average marks of the class is 60%. So the teacher thinks, okay, maybe some of the students have understood the concepts and some other students haven't understood the concepts. So let me teach the concepts again. Day 2, the teacher again teaches the same examples. in a slightly different way. This we can say as iteration number 2. Second time the teacher is teaching the students. And now, what do you think? As the number of iterations increases, that is, if the teacher keeps on teaching multiple number of times, don't you think that the students will be able to understand better? Obviously, the same concept, the same topic is being repeated. So obviously, the grasping capacity, whatever the grasping capacity of the students is, the students will be able to grasp even more. The second day, the students' understanding will increase. The third day, it will be more. The fourth day, it will be better. The fifth day, it will be even better. So maybe after the second day, the average marks of the test is 65%. Third day, fourth day, fifth day, sixth day, seventh day, eighth day, as you keep on training or as you keep on teaching the students, maybe on the seventh day, the performance of the students has increased to 90%. On the first day, it was 60%. The average marks of the class was 60%. On the seventh day, it has reached to 90%. So you can see as you retrain students, as you reteach students with multiple iterations, the performance increases. Similarly, in a machine learning model, a neural network model, a deep neural net model, or a linear regression model, or a non-linear regression model, as you keep increasing the number of iterations, the performance of the system keeps increasing. That is, the accuracy increases and the error decreases. This is something very important. So generally, uh, while retraining, what happens is the the machine learning model tries to find out relation between the independent variable x and the dependent variable y. And after finding out the relation, maybe it can predict. For example, if I give the machine learning model the prices of the houses for the last 2 years, and if I ask the machine learning model to predict the prices for the next 6 months, it may be able to predict it. So it's not necessary that the prediction will always be very accurate. Let us say I have trained a machine learning model with the prices of houses for the last 2 years. And now I want the machine learning model to predict the prices of the houses for the next 6 months. What will be the prices of the houses in April, May, June, July, August, September? I want the machine learning model to predict the prices of the houses. So the machine learning model will predict, so, okay, maybe in April it is 10 lakhs, in May it is 10.2 lakhs, in June it is 11 lakhs or something. It will predict some values. The predicted values are defined as or denoted as pi, and the actual values. So the machine learning model is saying in April the price of the house will be 11 lakhs. It may be 11 lakhs, it may not be 11 lakhs, who knows? When April comes, we'll see. Maybe the machine learning model says that the price is 12 lakhs and the actual price is say 13 lakhs. So P is called the actual value and P is called the predicted value and A is called the actual value. The difference between the predicted value and the actual value is nothing but the error. So neural network may also make some errors, and we want the errors to be as low as possible. For that, we need to design appropriate machine learning models. So P are the predicted values, A are the actual values. P minus A, predicted minus actual, will give you the errors. So error is nothing but P minus A. Now it may so happen that the errors may be positive as well as negative. For that, we generally calculate something called the mean square error. That is 1 by n summation of ei square I is equal to 1 to n. What do I mean by that? I'll tell you. So let us say these are the prices of the houses for the next 4 months. So the predicted value is 10 lakhs and the actual value is 9 lakhs. What is the error? 10 minus 9, that is 1 lakh. Say in May, the predicted value is 12 lakhs. Actual value is 10 lakhs. What is the error? 12 minus 10, that is 2 lakhs. In June, the predicted value is 15 lakhs. Actual value is 13 lakhs. What is the error? 13 minus 15 minus 13, that is 2 lakhs. In July, it's something important. The predicted value is 20 lakhs. Say the actual value is 25 lakhs. What is the error? 20 minus 25, that is minus 5 lakhs. So how will you calculate the total error? Total error is equal to error 1 plus error 2 plus error 3 plus error 4. What are the values? 1 plus 2 plus 3 plus minus 5, that is 0. Can you see the total error becomes 0? What is the average error? Error 1 plus error 2 plus error 3 plus error 4 divided by 4. So that is 0 divided by 4, that is 0. I'd like to point something very important over here. I'd like to plant a flag over here. The errors can have positive values as well as negative values. See, the error over here has a negative value, whereas these errors are positive. So the errors can be positive or they can be negative, positive or negative. If you add up errors like this, then the positive errors and the negative errors can cancel out. So it is better to square the errors and after that calculate the average. So 1 square is 1, 2 square is 4, 2 square is 4, minus 5 square is 25. So if I square the errors, then what will happen is the negative values will also become positive. The positive values, the square of the positive values are in any case positive, but the squares of the negative errors will also become positive. So in that case, you can avoid the cancellation of positive errors and negative errors. So in this case, see, if I square the errors, then calculate the average, then the error comes out to be 8.5. Why it is not recommended to calculate the total error or the average error like this? Because the positive errors and negative errors may cancel out and you may get a zero error. So for example, if I say my machine learning model has zero error, what does that mean? The machine learning model is making no errors. It is completely accurate. But is it the case? No, it is making errors, but the positive errors and negative errors are cancelling out. So scientists and data scientists always calculate the mean square error. Another way is to take the absolute value or the mod of these values, not take the sign. That is called mean absolute error. So mean square error is generally computed. That's a very important function. This is also called the objective function. This tells you the lesser the error is, the higher the accuracy is. So as you keep decreasing the error, the accuracy keeps increasing. As the error increases, the accuracy decreases. So now we'll come to the objective function. Okay. So over here, say on this slide, you'll see generally the objective function is considered to be the mean square error. What I have done is pi minus ai, predicted minus actual. This is the error. If I square it and if I calculate the mean, that is divided by n. N is the number of errors. Summation of I is equal to 1 to n pi minus ai. That means error 1 plus error 1 square, error 2 square, error 3 square, error 4 square. I'll add them up, divided by n. So this will be the mean square error. Generally, the mean square error is considered or called the objective function or the cost function. As we keep training a machine learning model, the cost function or the objective function keeps decreasing and the accuracy keeps increasing. So this is something important. As we keep training a machine learning model, the accuracy keeps increasing, the cost function can be considered to be the mean square error. Okay, is it okay? Can you people follow? Is it okay? Maybe it's a little mathematical. Is it okay?
Yes, sir.
Is it okay? Maybe it's a little mathematical. I hope you can follow. Okay. Okay. Anyway, if you have any problem, we can again discuss it later on. Anyway, so for example, objective function and gradient descent. So for example, in case you have a linear regression model, y is equal to mx plus c, or y is equal to theta 1x plus theta 2. In that case, you'll try to adjust the values of theta 1 and theta 2. That is, in case y is equal to mx plus c, we'll try to adjust the values of m and c in such a way that with each iteration, we'll try to minimize the errors. So E is the error, 1 by n summation of I is equal to 1 to n ei square is the mean square error. What this means is you'll try to adjust the values of theta 1 and theta 2 in the linear regression model in such a way that with increasing number of iterations, you'll minimize the error. So as you keep training the machine learning model, the error keeps decreasing and the accuracy keeps increasing like this. Okay, so this is what we try to do in a machine learning model. Generally, we retrain a machine learning model. As you retrain a machine learning model, generally the error keeps decreasing. Okay. So next is the case. There's something called gradient descent. Very important concept. Extremely important concept. Gradient descent or GD. The gradient descent. What I'll take a little, maybe 5 or 10 minutes more. Maybe I would have stopped at 1:30, but I think I'll need another 15 minutes, 10 or 15 minutes at the most, not more than that. So what the gradient descent does is, the gradient descent means as you keep training a machine learning algorithm, you keep training it, the error keeps decreasing and the accuracy keeps increasing. So there is something called a gradient. In case you have a linear regression model, the rate of change of error with respect to the value of theta, maybe theta 1 comma theta 2 also, theta 1 comma theta 2. So the rate of change of error with respect to the coefficients of the regression model, theta 1 and theta 2, gives you the gradient. And you want to decrease the error. So the gradient will reduce. So that is called gradient descent. In case of a neural network, you have got the weight and you have got the bias. So you will calculate the rate of change of error with respect to weight and the rate of change of error with respect to the bias. And your aim would be to keep reducing the errors and increase the accuracy as you keep training a machine learning model. I'm again telling you, a machine learning model may not find the patterns in the data if you give the data to the machine learning model only once. You may need to retrain the machine learning model. Okay, this is a very important concept. So this is a graphical representation of gradient descent. Let us say you are standing on the top of a hill and the error is very high. Error is very high. As you keep training, the machine learning model, the error keeps decreasing, 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 and you reach a point where the error is minimum. So what is your aim? To go down the hill, to descend the hill in such a way that your error keeps decreasing and reaches the minimum value as soon as possible, in as lesser number of iterations as possible. So this is the say visualization of gradient descent. Okay, what does gradient descent mean? It means nothing but continuously reducing the errors as you keep increasing the number of iterations for the machine learning model. Okay. So as we had seen the linear regression model, you can have a non-linear regression model. So in the linear regression model, what was the relation between x and y? Y is equal to theta 1x plus theta 2 into x. So y is equal to mx plus c, the form was this. In case of a non-linear regression model, it is also called a polynomial regression. For example, if it is third order, theta 0 plus theta 1 x cube plus theta 2 x square plus theta 3 into x. So you can see x can have higher powers also. So you can have a linear regression model. You can also have a non-linear regression model. Non-linear regression models will have generally higher powers of the dependent variable x. Okay, and theta 0, theta 1, theta 2, these are called the coefficients of the regression model. Now, something extremely important, extremely important, back propagation. Although I won't go into too much detail, but it is something extremely important, very important. So please pay attention over here. Generally, I told you the neural network generally has three layers. One is the input layer where the data arrives. One is the hidden layer where the processing of the data takes place, and one is the output layer from where you get the output. So generally, the data travels from the input layer to the hidden layer, and from the hidden layer to the output layer. Don't worry, I'll also cover this in much more detail in the next lecture as well. So just to give you an idea, generally the data comes to the input layer, the data goes to the hidden layer for processing, and from the hidden layer goes to the output layer, and you get the output from here. Okay. In the output, you may have some errors. The machine learning model may give you some errors in the output. It's not necessary that the machine learning model will give you no errors, zero errors. That never generally happens. Generally, you have some errors. You want to have as low a value of error as possible. If you feed back, the errors back to the machine learning model towards the input, then this is called back propagation. So this concept was basically put forth initially by three scientists, D. Rumelhart, Jeffrey Hilton, and R.J. Williams. So Rumelhart, there is a extremely famous paper by Rumelhart et al. Or Rumelhart, Hilton, and Williams called "Learning Representations by Backpropagation Errors." This was published in the 1986 issue of the journal called Nature. It's a very well reputed, extremely reputed research journal, Nature. And Rumelhart, Hilton, and Williams published that paper in which they introduced the concept of backpropagation. What they proposed was you have a neural network in which you feed the data. After that, the data is processed, and after that, you get the output. And in the output, you get some errors. Why not? Why not? Excuse me, just excuse me. Yeah, I'm sorry for the interruption. Maybe I forgot to put one of my cell phones on the silent mode only. So, what they suggested is you can do one thing. What you can do is you can feedback the errors from the output towards the input. It is something like this. For example, somebody is doing some job, and he's doing it or she is doing it, and there are some errors, some shortcomings in the job. If you don't give the feedback of the work to that person, then how will the person know what is going wrong? So, for example, I'm teaching. What do you know? What I'm assuming? I'm assuming that whatever I'm saying, maybe everything is correct and everything is very clear to you. But say some of you may face some difficulty in understanding the concepts. If you do not tell me, if you do not give me the feedback, if you don't point out the errors to me, then how will I understand what is my shortcoming? Okay, so this was the basic concept. So Rumelhart, Hilton, and Williams, for example, Jeffrey Hilton won the Turing Award in 2018 for deep learning. Great scientist. So this is the concept of backpropagation. So basically, in backpropagation, I'll cover this in more detail in the next lecture. Don't worry about it. Generally, in the backpropagation mode, what we do is we feed the neural network with the present input. We also feed the neural network the past error. So, for example, if I'm at iteration number k, I'll give the neural network the input of iteration number k. I'll also give the neural network the past or the previous error of iteration k minus 1. So the neural network has the inputs as well as the errors that it had made. Okay, this is the concept of backpropagation. This is maybe gradient descent with momentum. Maybe I'll cover this in the next lecture. I'll avoid it now because this is a little optional sort of thing. I won't go to this gradient descent with momentum. Rather, what I'll do is I'll give you the code for maybe the backprop. This is something important. This is the last coding example. So let us start with the coding example. So what I'll do is I've got another data. So just this is the last example. Okay. So is everybody with me? Can everybody follow? Is it okay? Last 5 minutes. Last 5 minutes. Is it okay?
Yes, sir.
Can everybody
Yes,
hear
sir.
me?
Yes, sir.
So okay, fine. Only last 5 minutes. So for example, I have got a data set over here, which has got two variables: age in years and height in centimeters. Okay. So for example, I have started the age from 5 years, 5 years, 5.0, 5.5 years, 6 years, 6.5 years, 7 years, 7.5 years, and the height. I've not put the height in feet, rather I have put it in centimeters. So, for example, as a child's age increases, the height also increases. If the age increases, the height also increases. So I want to find out a relation between the age and the height. Okay, I want to correlate the age and the height. I want to use a neural network with back propagation to find a relation between the age and the height. Let me see if I can do it. Okay, so this is the relation. This is the data actually. 5 years, 5.5 years, 6 years, 6.5 years, 7 years, 7.5 years, 8 years. The height is 120 centimeters, 124 centimeters, 126.4 centimeters, 130 centimeters something. I have actually arbitrarily created this data set for you, and up to age of 18, because maybe after 18 years the height generally stagnates. So maybe some people may grow after 18, but most probably the height doesn't increase much after 18 years. So this is how the height varies with age. Okay, I want to find a relation between these two variables. So let me see what I can do about it. So let me go to the code now. I hope my MATLAB command window is visible to everybody.
Yes, sir.
So first of all, what I'll do is close all. It will close all previous figures. Clear. Clear will clear all previous variables. Again, I'll use the XLS read command. XLS read age height XLS. So I've got an Excel sheet whose name is which I have named as age height, and the first column of the data set is the age, and the second column of data, as you saw, was the height. So let me try to first of all import this Excel file to my MATLAB command window. Let me see if I can do it. Yes, I have done it successfully. So this is the age, 5 years, 5.5 years, 6 years, 6.5 years, and so on. And after that, I've also, this is actually 1.0 into E02, that is 10 to the power 2, that is 120 centimeters, 124 centimeters, 120. So I have imported the age and the height. See, this is the age, and this is the height. Okay, so I have imported both variables. After importing both variables, what I'll do is, first of all, I'll say which is the independent variable and which is the dependent variable. So the age is the independent variable, and then height is the dependent variable. Generally, independent variables are also called represented as X or inputs, and the dependent variable is also represented as T or targets. So I'll first of all declare these variables. I'll declare age as X and height as T. So let me do that. So I've done that. After that, I'll use a training function. So basically, train LM. This is a training function. Basically, LM stands for Levenberg Marquardt. So maybe I'll write down the spelling for you. Levenberg, Marquardt. Actually, both are scientists, renowned scientists and mathematicians. This training function, this training algorithm is basically a backpropagation training algorithm in honor of Levenberg, Kenneth Levenberg and Donald Marquardt. So I've decided the training function to be the backpropagation training algorithm in honor of Levenberg Marquardt. So MATLAB has got a function named train LM. After that, I have say decided the hidden layers to be 10. I can take the hidden layers to be, say, for the number of neurons in the hidden layers to be 10. I can take the number of neurons in the hidden layer to be 5. It's up to me. Let us say let us keep it at 10. After that, what I'll do is net is going to fit net hidden layer size train function. So this is something what this line will do, what this code will line of code will do is it will create a network with 10 hidden layers and the training function train LM. After that, what I'll do is I'll divide the data. Generally, in machine learning, we divide the data into two categories. One is the training part and the other is the testing part. With the training data set, generally we divide into the ratio of 70 to 30. 70% for training, 30% for testing. Let us take one example. Suppose there is a teacher who teaches mathematics, okay, and in the book there are 100 questions. So the teacher, what will the teacher do? Maybe he or she will solve 70 questions on the board for the students to understand and train the students, and to evaluate the performance of the students, he or she will take a test. In the test, he or she will not give the 70 questions he had solved on the board. Rather, he or she, the teacher, will give the rest of the 30 questions. So 70% of the data of the questions have been used for training, and 30% of the data has been used for testing. So generally, we use this train ratio 70. This means 70% of the data out of the 100%, 70% of the data will be used for training. And again, 15% and 15% will be used for testing and validation. Validation means retesting. Sometimes we may want to retest something. So 15% for testing, and again 15% for retesting, which is also called validation. After that, we'll train the network. Network we had already defined over here, TR, that is training. We'll use the train LM command. So the net X and T. X, this net is the network, the neural network that we have created with 10 hidden layers and the train LM function. X are the inputs and T are the targets, that is the height. Okay. And after that, what we'll do will this command y should net x will give you the output of the neural network. It will tell you whether the neural network has been able to find a relation between the height and the age and the height. Whether the neural network has been able to find a relation, and it will give you the output of the neural network. And after that, see, this is something important. E is equal to G subtract T comma Y. What it will do is T is the target, Y is the output. This is Y is actually the predicted value and T is the actual value. So predicted value minus actual value will give you the error. Okay. Then we'll have the performance function. The performance is generally based on the mean square error. We'll try to find out what is the mean square error, and view network. We'll view the network and we'll have some plots, the performance plot, the scatter plot, regression plot, etc. Okay. So let me try to run this code for you. This is a very important example. Okay. So the neural net is busy. The computer is busy right now. It's computing. After the computation, okay, yes. Now see all the graphs over here. What has happened? Let me explain all the graphs to you. So I hope my screen is visible to everybody. Is my
Yes,
screen
sir.
visible to everybody?
Yes, sir.
Okay. So let me see what we have done, what we have achieved over here. So this is the neural network that we have created. So there is one neuron, or there is one input. Obviously, there is one input because we have got only one variable, that is the age. And we have got only one variable as the output, that is the height. We are trying to map the age and the height. Okay. So one stands for one input and one in the output stands for one output. The input is the age and output is the height. W are the weights of the neural network. B is the bias of the neural network. There are 10 neurons in the hidden layer. Okay. Data division. The data has been divided randomly from the entire data sets. 70% of the data has been taken randomly for training. The rest of the 30% has been taken randomly for testing. The training algorithm is a backpropagation based Levenberg marketed algorithm. The performance of the system will be calculated in terms of, or evaluated in terms of, the mean square error. The calculations will be done in the MEX format. How many iterations did the neural network take to train itself? 9 iterations. So in the first iteration, the neural network was not able to find the patterns between the heights and the age. Okay, so it took 9 iterations: first time, second time, third time, fourth time, fifth time, sixth time, seventh time. So it took 9 iterations for the neural network to train itself, for the errors to stabilize. The time taken was just 0.1 second. So no, it was 0001. That is 1 second only. 0 hours, 0 minutes, and 1 second only. So the training happened in 1 second. Performance. What was the mean square error? The value of mean square error is 0.0338. What is the value of the gradient? 1.15. I told you what is the gradient in gradient descent. Del E by del W, gradient descent. What is the value of mu? 0.00100. Now, what is this mu? Mu is also called the combination coefficient. Mu signifies the amount by which the weight changes in each iteration. And the validation checks. Validation check means how many number of times the neural network has found the error to be stable before stopping the training. So it has rechecked and cross-checked the output 6 times. For example, let me give you an example for it. Suppose you are, say, solving a problem and you have got some answer, but you are not sure about the answer. So what you do, you recheck it. Okay, let me check my solution again. So if you check it 6 times, that means you have validated it, or you have undertaken 6 validation checks. So neural network, when the errors keep fluctuating in real-time data sets, the neural network keeps on checking it, rechecking the results. That is called validation checks. Okay. So this was the training part. This is the neural network that you have created. One input, one output. This is the weight, this is the bias, and 10 neurons in the hidden input, in the hidden layer. And this is something important. This is the graph for the mean square error. You can see this axis has got epochs. Epochs means number of iterations. Y-axis has got the objective function or the error cost function. You'll see as the number of iterations increases, the error keeps decreasing. See, the error keeps decreasing, 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 decreasing. You have got three graphs over here, three curves. One is the training curve, one is the testing curve, and one is the validation curve. Training is when you are training the neural net. Testing means when you are testing the neural net, how is it performing, and validation is rechecking again. So you'll see uh, there is something written over here. I'll tell you what it means. For example, you'll see uh, best validation performance 3.3533 at epoch 3. What this means is while training, the mean square error kept decreasing with the number of iterations. See, it keeps decreasing. When the neural network was testing the neural net, it saw after the third iteration, the error became almost constant, not completely constant, but almost stable. So from the third iteration onwards, third, fourth, fifth, sixth, seventh, eighth, ninth, for 6 iterations, it found the error to be almost stable. That is why at the ninth iteration, it stopped the training. So generally, the training stopped either when the error becomes stable or the maximum number of iterations which you have decided is over. For example, you may say, I'll decide the maximum number of iterations to be 1000. So after 1000 iterations, anyway, the training has to stop. But before that, if the error becomes stable, we can stop the training. So this is the performance plot. After that, yeah, these are the training states. So in this, you will see as the number of iterations increases, the gradient, you'll see there is a decrease in the gradient. So what I had told you, the gradient descent. See, you can see the gradient descent over here. The gradient keeps decreasing. This is the value of mu. Mu is the combination coefficient, the amount by which the weights change. This is the combination coefficient. And this is the validation check. See, after the third iteration, fourth, fifth, sixth, seventh, eighth, ninth. For these 6 iterations, the error has become almost stable. That is why the neural network has stopped the training after the ninth iteration. The same thing can be seen over here. See, after the third iteration, the error becomes almost stable. Neither does it go upward nor does it go downward. Almost stable. So it stops training after the ninth iteration. And after that, yeah, you have got the regression plot. See, now see what the neural network has been able to do. The neural network has been able to find a relation between the age and the height, and the value of the regression is 0.99874. I told you the maximum value of regression is 1, which means complete similarity. Complete similarity means if you can find the relation perfectly without any error, but 0.9987 is also very close to 1. And finally, this is the last graph. This is the last graph. So you see the dots are the targets and the crosses are the outputs. The targets mean the actual outputs, actual heights, and the outputs mean the predicted values. So you can see the predicted and the actual values are very close and the errors are very less. That is why you're getting a regression value of 0.998. So this is how, I'll just summarize. You have created a neural network, you have trained it, you have divided the data, 9 iterations, 1 second, value of performance that mean score is 0.338 only, 6 validation checks. After that, this is the neural network that you could create. After that, this is how the mean square error of the cost function was reducing. After that, this is the training state, how the gradient is changing, how the validation checks are taking place. After that, the regression value, the similarity between actual outputs and predicted outputs, it's very high, 0.99874. And finally, you'll see the predicted outputs and the actual outputs are very similar in nature, very close, and the errors are very less. Targets minus outputs, this will give you the error. The errors are very less. So this is how you can train a back propagation based neural network using gradient descent. I have not covered gradient descent with momentum in this class. It's a little advanced concept and not required as of now. Maybe I'll touch upon it in the next session. Okay. So here and it. So let me come back to the presentation then. So these are some of the mean square error. I've told you accuracy is generally 100 minus error percent. So these are some additional parameters that we'll see. And I've not actually covered gradient descent with momentum. This is optional basically. So back propagation we have covered. So this is what we have covered in this section. So we had started with activation functions, linearity, non-linearity, its significance, significance of bias, weights, and combination coefficients. We have seen regression, we have seen back propagation, we have seen gradient descent. We haven't covered gradient descent with momentum. We'll cover this in the next session. And after that, we have plotted activation functions. We have seen what is the significance of the bias and the weights. We have seen linear regression. We have seen non-linear regression. We have seen it's not always necessary that you'll be able to model or fit the data as a linear regression model. After that, we have implemented back propagation and gradient descent, and it was a forecasting model. So given the age, can you predict the height? So we have covered this much. So I hope things have been a little, I hope you have understood a little bit about say machine learning now with some practical examples. I'm not assuming that you have understood everything, although I hope that you have understood something. But in the next session, you'll get even more examples and we'll be starting with deep learning. So thank you for your patient hearing. Does anyone have any query? If you have any queries, you can ask me. Does anyone have any query?
Yes, sir.
Yeah, please tell me.
Sir, if by the number of hidden neurons will not affect the output, as you said that the it is up to us that how many number of hidden neurons we are keeping in the.
Yes, yes. So basically, it's a very interesting question that you have asked me. So generally, I'll just give you one example. I'll quickly maybe try to answer your question. So generally, what happens is, yeah. So generally, the number of neurons in the input is equal to number of input parameters that you give. For example, if you give only one input parameter, age, then you can have only one neuron at the input. If you have only one output, that is the height, you can have only one output neuron. But what about the number of neurons in the hidden layer? So,
Yes, sir.
generally, there is no fixed rule or there is no mathematical formula in machine learning that will tell you the number of hidden layers or the number of hidden neurons to keep in the hidden layer. It has to be done based on a trial and error basis. Generally, what we do is generally we start with three or four maybe neurons in the hidden layer, or maybe we go up to 10 or 15. So generally, the simpler machine learning models, for example, when the data set is not very large, when the data is not very complex, generally maybe 5 or 10 neurons in the hidden layer will suffice. That is sufficient. Generally, as you keep increasing the number of neurons in the hidden layer, the complexity of the algorithm keeps increasing. Okay, the complexity keeps increasing. So that is why we do not, pack in a lot of neurons in the hidden layer. Rather, when you will come to the next session, you will see something called deep neural nets and deep learning, in which you have multiple hidden layers. Hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4, hidden layer 5, stacked one after the other. And each of the hidden layers will have multiple number of neurons. So as far as your question goes, the number of hidden layers, the number of neurons in the hidden layers depends on the designer, the programmer. Generally, as you keep increasing the number of neurons in the hidden layer, the accuracy of the system may increase up to a certain point, but after that, not much of an improvement is seen in the accuracy. So that is why we generally try to keep the neurons in the hidden layer up to maybe 5 or 10 or something, and not increase too much. If the complexity of the data is too high, then we rather go for a deep neural network with multiple hidden layers rather than packing up too many neurons in the hidden layer itself. So it
Okay,
basically
sir.
depends on us, and there is no formula which will tell you the number of hidden layers to use. It's up to you. It's basically decided on trial and error.
Okay, sir. Thank you, sir.
Yeah, thank you. That was a good question. Yeah. And anybody else? Any other question? Okay, then I suppose, yeah. If anybody else has any problem or any question, you can also ask me in the next session. So the next session will be the last and concluding session in which we'll be looking forward to deep learning. So I thank you all again for your patient hearing and giving me your valuable time. And I'll see you in the next session. Okay. And I'll request you to go through the contents of this session as well. You'll have the recorded videos and the recorded video and the code snippets. I'll share the code snippets with you. Okay. Right.
Thank you
Yes,
very
sir.
much, sir. Thank you very much, sir, for essential information
Thank you. Thank you. Thank you
guidance.
so much. Yeah, yeah, sure, sure.
On
I'll see.
behalf of the
Yeah.
yes, sir.
Yeah. You have continued. Yeah. Please go ahead. Yeah.
Thanks. On behalf of entire institute, I would like to thank our honorable guest for his presence and inspiring words. And also, I want to thank the students and faculty members for their cooperation. Thank you very much.